Good morning children. Welcome to your chemistry online class. Last class we have discussed about S block elements. From today onwards we are starting a new chapter, that is P block elements. What are P block elements? Do you know? The last electron enters to the p subshell of these elements. That's why they are known as P block elements. How many P block elements are there? Do you know any speciality of these P block elements? Yes, we are studying about the P block elements, mainly boron family and carbon family. Let's start.
Group 13 elements are known as boron family. Why? Because the first member of in the group is boron. So the entire group is known as boron family and it consists of the elements boron, aluminium, gallium, indium and thallium. And if you check with this group, aluminium is the most abundant metal on earth. And aluminium is the third most abundant element in the earth crust. Okay. So aluminium is really important thing in our daily life too. If you check with the electronic configuration of boron family, and you can see that the last electron is entered to the p subshell. That's why it is known as p block element, and the general electronic configuration will be ns2 np1. If you check with boron, it is 2s to 2p1, aluminium 3s to 3p1, gallium 4s to 4p1. So generally we can write it as ns2 np1. Yes, ns2 np1. And the stable oxidation state plus 3 and decreases as we move down the group due to inert pair effect. What do you mean by this inert pair effect? This is reluctance of ns2 electrons to take part in bonding due to the poor shielding effect of interweaving d and f orbitals on moving down the group is known as inert pair effect. For example, if you check the structure of gallium and indium and thallium, in the case of boron and aluminium, there is no inert pair effect because there is no d subshell. And if you check with gallium, indium and thallium, we can see here d element, d block also, the d subshell also there. And for indium also d subshell is there. For thallium, f subshell also and d subshell. So what we'll do is the inner shells are d and f shell. So they will shield the outer shells. So the nuclear attraction on the outer shell will shield by the inner shells. Due to this S block, this S subshell and will not readily undergo reactions. They will not take part in this reaction. This is known as inert pair effect. The P block elements will show inert pair effects. You can see here a representation of the inert pair effect. Then we'll see the atomic size. How the atomic size vary down the group. And if check, we know the general trend of atomic size. While moving down the group, atomic size increases. Moving left to right in the periodic table, the atomic size decreases. These all things we know. So the same effect you can see in the boron family. If you check with the boron family, the general trend in atomic size moving down the group from boron to thallium, atomic size increases. Why? Because the atomic number increases, number of shells increases, hence the distance from the nucleus to the last shell, that is atomic radius, that also increases. This is the general trend in atomic size in boron family. While moving down the group, atomic size increases. Here you can see the atomic radii. However, if you check here, there you can see a difference from if according to the general trend it should be increases, no? So but it is increasing, but in the case of aluminium and gallium, there you can change there you can see a change compared to aluminium, gallium having less atomic radius. Why? It is because due to this inert pair effect. It is due to the poor screening effect of interweaving intervening d orbitals. That's why there is a slight difference. Then we'll see ionization enthalpy. We know general trend in ionization enthalpy is while moving down the group, ionization enthalpy decreases. But in the case of boron family, the ionization enthalpy values do not decrease smoothly down the group. Here you can see the ionization enthalpies. This is the first ionization enthalpy. So while moving down the group, it is decreasing, but in the case of thallium compared to indium, it is more. So it is not, there is only slight difference. The current trend or correct trend we cannot see here. It is also due to the poor screening effect of D and F electrons. And the first ionization enthalpy is less compared to second and third. And the sum will be very, very high. We'll see electronegativity. While moving down the group, the electronegativity decreases. From boron to aluminium, it is decreases. From aluminium, it is increasing. It is also due to the different atomic size of the atoms. And we'll see the physical properties. If you check with this, boron is hard, black colored, high melting, non-metallic solid. But all others are soft metals which are having low melting point and high electrical conductivity, that is, it will conduct electricity so easily. And density increases down the group from boron to thallium. And gallium is very useful material for measuring high temperature as its low melting point and very high boiling point. And we'll see the oxidation state. Except boron, all other are metals. Boron, why boron is showing some anomalous properties due to its small size and high ionization energy. And it's having the ability to form covalent compounds. Aluminium forms plus 3 cations, so the oxidation state is plus 3. Gallium, indium and thallium all form plus 3 cations, but also plus 1 cation. So boron will show the plus 3 oxidation state, aluminum also show plus 3 oxidation state, and gallium, indium, thallium, the lower last members, they will show both plus 3 and plus 1 oxidation state. So their stability will be in the plus 1 oxidation state. The stability increases as we move down in the group due to inert pair effect. So thallium is more stable compared to aluminium. And BF3 and AlCl3 etc. behave as Lewis acids. That is, they are electron deficient compound. So the tendency to behave as a Lewis acid decreases in a group due to the increase in size down the group. So BF3 and AlCl3 will be more, they will show the property of Lewis acid. Then we'll see the chemical properties. First one is reactivity towards air. Boron is unreactive in crystalline form. Aluminium forms a very thin oxide layer on the surface which protects the metal from further attack. But if you check with iron and all, we know the corrosion of iron, but aluminium first form a thin layer, then this thin layer protect the other metals from this type of corrosion and all. Amorphous boron and aluminium metal on heating in air form B2O3 and Al2O3, they are dimers. You can see the general formula of dimer here. The oxide. These oxides are basic in nature. While moving down the group, the basic nature will increases. And boron trioxide, it is acidic. Aluminium and gallium oxides are amphoteric. Indium and thallium are basic in their properties. So first member is acidic. Aluminum and gallium are amphoteric. Amphoteric means it will show both the properties of acid and base. Reactivity towards nitrogen. Only boron and aluminium forms nitrates at a high temperature. All other boron family members will not show this property. Reactivity towards acids and alkalis. Boron does not react with acids and alkalis even at moderate temperature. Aluminium shows apophotic character, and aluminium dissolves in dilute acids and alkalis and liberates hydrogen. In concentrated HNO3, aluminium becomes passive by forming protective oxide layer on the surface. And aluminium dissolves in dilute acids and alkalis and liberate hydrogen. Here you can see aluminium dissolves in acids even though dilute acids, and it will form aluminium ion and alkalis and hydrogen also. Reactivity towards hydrogen. These elements react with halogen to form trihalides except thallium. Here it is the boron. General any element from boron family represented by the letter E. When it reacts with halogen, halogen is represented by the letter X. It will form trioxides, that is trihalides, 3 halogens. For example, BCl3 or AlCl3 and AlBl3, etc. Reactivity towards halogen. These elements react with halogen to form trihalides also. Even that we have discussed already. And if you check with the boron, boron shows some anomalous properties compared to other elements. Why it is showing anomalous property? Because it is having very small size, as it is the first member, and it is having high electronegativity, and it will form covalent compounds. Why it is showing this? Because it is doesn't having a d orbital. And this we can this anomaly properties of boron is it is also similar to the next member in the second group. This relationship is known as diagonal relationship. This we have already studied in the previous chapter. So this is all about the boron family. And some other important compounds. This portion is deleted from the chapter. So only you have to study about these important things of boron. What is boron family? What are the members? What are the physical and chemical properties of boron family? These all about the chapter.